This video is about the cornea, a very remarkable structure. The cornea is the clear window that lets light into the front of your eye. In this video we are going to explore several of its amazing properties. First, it is made out of the same tissue as your skin. So how is it the cornea can be so clear? Second, optically speaking, the cornea supplies more than half of the focusing power of the eye. Third, the shape of the cornea has to be perfectly smooth and properly curved to make the high-quality image that falls on the retina. We will explore all these features in detail. Looking at the front of the eye, some parts are easy to identify. You can see the iris, the colored part, and the pupil, the round hole in the middle of the iris. The cornea, however, is so clear it can only be seen by the light reflecting off its surface. This is the view we get looking through the microscope that we use to examine the eye. The pupil is widely dilated, with a slit beam of light passing through the cornea and lens. Each is outlined with dashed lines to make them easier to identify. In diagram view, the cornea is like the crystal of a watch arching over the iris. In the center of the iris is the pupil, which changes size to regulate the amount of light entering the eye, and behind the iris is the natural lens, like the lens in a camera. If the slit beam view was confusing at first, it should now make more sense. You can see the curved shape and thinness of the cornea, separated by a space, then the rounded shape and thickness of the normal lens. In the adult, the average cornea is 12 millimeters wide. Thickness in the center is half a millimeter, at the edge 0.7 millimeters. Think about that, only half a millimeter thick. Looking closer at the cornea, we are taking a section and magnifying it, showing it has three distinct layers. On the outer surface is the epithelium, a lot like the surface layer of your skin. The middle layer, the stroma, occupies most of the thickness of the cornea, providing its shape and structural integrity. Lining the inside is the endothelium, a single layer of cells that pump fluid out of the cornea, keeping it dry and clear. Looking through a regular microscope, you can see the actual corneal layers and the fine cellular details. We will now work our way from front to back in detail. The first thing that light encounters as it reaches your eye is the tear film on the surface of the cornea. A good quality tear film is important for clear vision, comfort, and corneal health. The tear film needs to be smooth and even, say glassy, as the first step of making a clear image. If it is not smooth, then light is scattered and vision is reduced. The tear film is more complicated than you might guess. Magnifying the section in the orange circle shows the tear film has three layers. On the surface of the cornea is a layer of mucus. That allows the watery part to spread out over the cornea. In the middle is the aqueous or watery layer. On the outer surface is a layer of oil which helps reduce evaporation. So, the tear layer is more complicated and more important than you might have thought. Back at the microscope view, we see the outer surface layer of the cornea, the epithelium. In this closer view, you can see the individual cell layers, which are labeled. Epithelial layers typically rest on a basement membrane. That is important because that is where the epithelial layer makes its attachment to the cornea. The epithelial layer is derived from the same tissue as your skin, so it behaves much like your skin. How is that? The action begins in the column-shaped basal layer of cells. These cells divide and move upward into the middle layer, where they take on a more flattened wing-like shape. Then they reach the surface, and after a short while they are sloughed off, just like dead skin cells. This process takes about 7 to 10 days, meaning the surface cells are replaced just about every week. In the big picture, the growth pattern of epithelial cells behaves according to the XYZ rule. X. Basal cells divide and migrate upward. Why? Basal cells come from a reservoir of stem cells located at the edge of the cornea, the corneal limbus. At the limbus, the stem cells divide and become basal cells which migrate horizontally toward the center of the cornea. Z. The surface epithelial cells migrate to the lower center before they slough off, in some cases leaving a cloudy double Y shape. Pretty cool how all that works. Beneath the epithelium is the stroma. The structure and strength of the cornea is based on layers of collagen fibers that make up the stroma. In the center, the fibers are oriented in different directions in different layers, while around the edge they run circumferentially. The layered structure affects how the cornea responds mechanically to surgery, which is nicely described in an article, quote, "The cornea is not a piece of plastic," end quote. That is important in refractive surgeries like LASIK. In the front, the fibers are more adherent, therefore stiffer, while in the back they are more flexible. The stiffness in front helps the front surface maintain a stable shape, which is of key importance to its optical/focusing properties. We will talk more about those properties in a minute. But first, this is a good place to appreciate the remarkable clarity of the cornea. Over 95% of the light hitting the cornea is transmitted through, which is why the only way you see the cornea is by the reflections from the surface. The most common explanation for its clarity has to do with the very orderly arrangement and spacing of the collagen fibers. You get a feel for that in this closer microscope view. Beneath the stroma is the innermost layer of the cornea, the endothelium. Though it is only one cell layer thick, it is nevertheless quite important. Your eyeball has a certain amount of internal pressure that keeps it inflated and functioning properly. That inflation pressure pushes the watery fluid in the front chamber of the eye into the cornea. If this was unchecked, the cornea would fill with fluid and vision would be cloudy. The endothelial cells pump that fluid out of the cornea, keeping it relatively dry and clear. A very important function. Technical note: cells do not actively transport water. Instead, they pump sodium and potassium ions, and water follows the osmotic gradient. In addition to the corneal layers we talked about so far, there are 3 layers we didn't mention. At the front of the stroma is a denser layer of collagen called Bowman's membrane. At the back of the stroma is Descemet's membrane, the basement membrane of the endothelial layer. Last spring, a new layer was described called Dua's layer, a dense layer of collagen just on top of Descemet's layer. Kind of an event when a new piece of anatomy comes along. In addition to its amazing clarity, the cornea has to maintain a very stable and precise shape because it also is an important part of the eye's focusing system. You might think that the lens supplies the focusing power of the eye, but that would be less than half right. When light hits the tear film, the curvature of the surface and change in index of refraction causes the light to bend. Then it hits the lens with a different index of refraction and it bends a bit more, finally coming to a focus on the retina. The focal length of the eye is about 22 millimeters. As an approximate calculation, it takes about 60 diopters of focusing power to focus an image on the retina. About 20 diopters comes from the lens, while 40 comes from the cornea. The lens, though it has less focusing power, has the ability to change its focus by changing shape, a marvelous ability which is covered in other videos. To give you a feeling for the focusing power of the cornea, consider what happens when you open your eyes underwater. Everything becomes very out of focus. The air-to-tear interface is lost, so no light bending occurs, and 2/3 of your focusing power is gone. Put on a set of goggles, and the air-water interface is restored, along with vision. If you haven't studied optics, you might think that a typical lens, or focusing surface like the cornea, would have the nice round shape of a sphere. Unfortunately, a sphere, though a pleasing shape, does not produce a very good image. In a spherical lens, light rays coming through the center of the lens are focused at one place, while those coming through the edge focus at a different place. The image quality is poor. This is called spherical aberration. The ideal lens shape is a parabola where all parallel light rays, both from the center and the edge, are focused at exactly the same spot, producing a good quality image. It turns out the cornea is close to, but not exactly a parabola. Technically, it is a prolate spheroid, steeper in the center, flatter at the edges, with a small amount of positive spherical aberration. In youth, this is offset by the lens, which has a little bit of negative spherical aberration. They come close to canceling each other out, and a high-quality image is produced. These shape details turn out to be important in the design of intraocular lens implants and the target profile of LASIK surgery. Another kind of aberration is astigmatism, meaning the curve of the cornea is not the same in the up-down direction as in the side-to-side direction. Picture it like the oval shape of a football. In this example, horizontal rays coming through the steeper meridian are focused in one place. Vertical rays coming through the flatter meridian are focused in a different place, further back. Again, this results in reduced image quality. Astigmatism then is not a disease. It only refers to the condition of not having equal curvature on different meridians. As long as the surface is regular, it can be corrected by glasses prescription. There are other aberrations, but they are less important and we are not going to discuss them here. Also, we have only talked about the front surface of the cornea, but the back surface in the lens can also contribute aberrations. In summary, though your cornea is made out of the same tissue as your skin, it is remarkably clear. This is due mostly to the regular arrangement and spacing of collagen fibers. We looked at the different layers of the cornea and what each did from surface to inside in detail. Last, we looked at how important the cornea is in creating a sharp image on the retina based on focusing power and a smooth, regular surface of a specific shape. The end result is a structure with several remarkable properties. In the next video, we're going to cover common surgeries of the cornea. First, if the cornea becomes cloudy or distorted, that can often be remedied by a corneal transplant. Second, because the cornea is so accessible, it is an easy target for attempts to change glasses prescription. In other words, refractive surgery, like LASIK.